Ren. So we're starting to come to the end. This is our second to the last test, depending, well, this depends on the order that you actually watch them. This is the second to last one I'm doing. This is the ratio test. Um, and this test really comes in handy when you kind of have crazy things like these factorials in your um, series. And if you don't remember, a factorial is just a sequence of multiplication, the product of every term prior to the actual factorial. So 5 factorial means 5 times 4 times 3 times 2 times 1, right? 100 factorial is times 99. I'm not going to write these out, obviously. But I want you to see the relationship. If I did n minus 1, the only difference between, say, 100 factorial and 99 factorial, right, is that multiplication of 100. So in order to do work with the ratio test, you do have to understand factorials. And factorials isn't something you've worked with a lot up to this point in your math classes. So let's look at it this way. Thinking about that 100 and that 99, what if I had n plus 1 factorial over n factorial? What does that look like? Well, n plus 1 factorial is n plus 1, right? Well, I got to go one less. One less is just n times n minus 1 dot dot dot. What does n factorial look like? Well, it's n times n minus 1 dot dot dot. So you can see a lot cancels away. So that's what I want to make sure you do understand how to do before we get started with working with any factorial in a series, is you understand that n plus 1 factorial over n factorial is simply n plus 1. So you might have to do some different type of canceling with factorials, and I just want to make sure you understand what they look like. So again, if you see factorials, not something we can integrate or really do much at all with. The other thing you see is things like n to the n. What does n to the n look like? Well, that's 1, right? 2 squared, 3 cubed, 4 to the 4th, 5 to the 5th. These kind of terms aren't something we're used to working with. When you see terms like this is when you start to think, maybe I should apply the ratio test here. Okay? So again, let's talk about what the ratio test is. So ratio test can be applied as long as you have a series of positive terms. Okay, so you don't have any negatives in there. The last test we're going to talk about, which is actually 10.6, our alternating series test, so you're going to see that is a series that has positive and negative terms in it. But a ratio test can only be applied if you have a series of positive terms. And what you're really doing is you're going to examine, not look at, examine the ratio of two consecutive terms. And it's very specific to consecutive terms. So it's not like the limit comparison test where it didn't matter that ratio, whether we put our original series A sub n over B sub n or B sub n over A sub n. We just needed to know we got a constant, a finite positive value as an answer. This one's going to matter. So what you are going to do is take the limit as n goes to infinity of the a to the n plus 1 term over the a to the n term. and you're going to examine that limit. Okay, so basically, we're picking a random term, a general random term, and we're going to call it a to the n plus 1. We're going to divide that by a to the n, and we're going to see what that limit is. So here's the deal. 1, if the limit is less than 1, it converges. All right, if the limit is less than 1, then according to the ratio test, your series converges. If the limit is greater than 1, it diverges. Okay, so limit being less than 1, it converges because your denominator, just think about how the fraction is going to work. It just has to do with how fast it's kind of growing. But here's the issue though. If your limit equals 1, yeah, the ratio test is inconclusive. So if you try a ratio test and you get it equal to 1, that means another test could be applied to that particular problem. It's not going to work. So let's just take a look at one. So again, less than 1 converges, greater than 1 diverges, and then inconclusive if it actually equals 1. All right, so remember I said this test works when we have, let's do 2 to the n over n factorial. All right, so it's that factorial that's going to kind of trigger you to say, I've probably got to do a ratio test here. You can try other tests. Like if you were to try, on all of these that you get in front of you, remember the first thing we said is you always want to try divergence test. Well, if you take the limit, the divergence test is easy to kind of look at. You're just taking the limit of that. We learned that n factorial is a really fast growing. It's much faster than 2 to the n. So that actually goes to 0, and we know the divergence test is inconclusive when it goes to 0. So you start to think of other tests integral test. To do an integral test, well, you actually have to take an integral, and I don't know about you, but I don't think at any point in its course so far we have taken the integral of n factorial. So that's not going to work for you. Your comparison tests don't really work, so because what exactly are you going to compare it to? Anyway, at this case, that factorial triggers, I'm stuck with a ratio test. So let me do my ratio test. All right, so I need the limit as n goes to infinity. Now the denominator has to be a to the n plus 1. So that means I'm just going to go to my series and replace my n's with n plus 1. So that's 2. Let me move this a little bit. All right, 2 to the n plus 1 over n plus 1 factorial. And I'm going to divide that by a to the n, which is 2 to the n over n factorial. As we learned in the limit comparison test, though, we don't usually start writing it out this way. When we have these ratios we have to write, isn't it much easier? You do not need to show me that first one, to just simply write them as 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. All right, so we need to find this limit, and it's actually a lot easier than you realize. Hopefully you start to see some similarities, and if you want to, we can even rewrite it. We don't have to, but I'm going to rewrite it. Not doing anything but rearranging a little. So I'll group the 2 to the n plus 1 over 2 to the n together, and I'll group the n factorial over n plus 1 factorial together. All right, so again, we haven't taken a limit yet, but we're going to certainly reduce it. So what is this going to give me the limit of? Well, you have the same base in the twos. You know, you do exponent numerator minus exponent denominator. So n plus 1 minus n is simply 2. So that's just 2. N factorial over n plus 1 factorial. Well, we did that. Here, I'll scroll up for a minute. Yeah. Wherever the n plus 1 factorial is, you're left with just an n plus 1. So remember, this, and if you're not sure, just expand it out a little. This is n times n minus 1 times n minus 2, dot, dot, dot. And n plus 1 is n plus 1 times n minus 1, dot, dot, dot. So the n minus 1's all cancel. The n cancels, sorry. And what are you left with? You're left with an n plus 1 in the denominator, so be careful. Well, there you are. You're left with a limit that you can easily take. As you know, 2 over n as n goes to infinity, that if your denominator is growing at a much faster rate than your numerator, then your limit goes to 0. And we're fine because according to this, your limit is less than 1. So we converge. And that's it. You would say because L is less than 1, we converge. So we'd say by the ratio test, and again, that's all you need to tell me because you showed me all the work up here. Whoops. My pen decided to stop working. Hold on. So I have 2 pens. The battery went on 1. So let me finish this up by the ratio test. A to the n. Converges. That's it. So we'll take a look at one more. Because I said it's not only with factorials. Ratio test can also be used. I mean, ratio test can be used with anyone. Anything, as long as, don't forget, I'll scroll up, as long as it's a series of positive terms. Okay? But some of your series get quite complicated, and using the ratio test can be a little complicated. But again, very similar series, but not quite. N to the n. Same idea. All right. So I'm going to use a ratio test here. And again, you can, when you're taking the test, you might, I always say, oh, you should always try the divergence test. But if you see something like this, you see a factorial, you probably just want to jump right to the ratio test. Because n to the n is going to go to infinity much quicker than 2 to the n. So that ends up being 0 if you try the divergence test. So that's eliminated anyway, and that's inconclusive. But the ratio test. So I need first to start with a to the n plus 1. So what does a to the n plus 1 looks like? 2 to the n plus 1 over, n plus 1 to the n plus 1. It's a bit complicated. All right? Because I have to replace all my n's with n plus 1. Now, for the b to the n, I'm going to multiply by, not the b to the n, sorry. I'm not doing the limit comparison test. For the a to the n, I'm going to multiply by 1 over its reciprocal. So it's n to the n over 2 to the n. So again, to make this a little bit easier, I can rearrange. You might want to do that. That's up to you. And I'm going to put 2 to the n plus 1 over 2, 2 to the n times n to the n over n plus 1 to the n plus 1. Okay, so now, this is where this test gets a little complicated, but this is one of those things that you may never have figured this out on your own, but now that you see it, hopefully you'll see it elsewhere if you need to. Little bit more complicated. The 2 to the n plus 1 over 2 to the n is fine because we do n plus 1 minus n. Again, that's just a 2, right? Here's the part I want to take off and play with for a minute. All right, let's look at this before we put it in there. Yeah, there's a bit of manipulation we have to do to this one to get it to something that makes sense to us where you can actually take a limit. The first thing I'm going to do is rewrite the denominator. So what is n plus 1 to the n plus 1? Well, if I pull out an n plus 1, then I'm left with n plus 1 to the n power, right? Because n plus 1 times n plus 1 to the n is n plus 1 to the n plus 1. Okay, well, that's something. If I do that, I can simply come up to my limit and put that n plus 1 over there, right? I can move that with the 2. So now what am I left with? So now I'm left with n over n plus 1 to the nth power. So I took this piece and said, you know what, I'm just going to go ahead and pair that with my 2 and leave it out of what I'm dealing with right now. I'm still trying to figure out what this is. So here's the deal. And this is where it gets tricky and you may not remember this. But do you recall that the limit as n goes to infinity of 1 plus 1 over n to the n is? Hopefully remember that is e. But what's another way of writing 1 plus 1 over n to the n? Well, isn't that the same as the limit as n goes to infinity? I'm going to combine them as one fraction. I'm going to turn 1 into n over n. Well, that also equals e because we didn't really change anything. So now, what's the difference between this and this? It is reciprocal. Yeah, it's a reciprocal. So what does that tell me? It tells me the limit of n over n plus 1 to the n equals 1 over e. And I can use that. So how can I use that? Well, let me go back to what I have in my limit now. I have 2 over n plus 1, right, times n over n plus 1 to the n. Well, when you plug in infinity, the first one is simply going to go to 0, right? Because you have 2 over infinity. When you plug in infinity to this second one, you get 1 over e. So that is just 0. I know it's crazy. Again, this right here is something you want to be able to recognize. But now I'm adding another piece where you need to recognize the reciprocal. When you have a limit, n over n plus 1 to the n is 1 over e, where the limit of n plus 1 over n to the n is e. And when I say you need to recognize these, not necessarily for our test, but you need to recognize these for any other math course you take moving forward. Okay? Anyway, our limit comes out to 0. Let's try to remember what we were doing. We were doing a ratio test. And when the limit is 0, we're fine, and our series converges. So L is 0, which means L is less than 1, converges, and rewrite by ratio test. Our series converges. Done. All right. So that's your ratio test. I know that one was a little bit harder. But again, you wouldn't see it on your own, but now you've seen it in case it comes up in any of your math lab problems. I think you should be able to work it out. Okay.